Okay. The Zoom is recording. My mic is working. Before we get into today's lecture, last week we had our first lab meeting. It was focused on lab safety. During the lab safety meeting on Friday, you were all given 2 assignments. Number 1, the lab safety quiz. Remember to complete that before Friday, 8:30 in the morning. It's due by the start of your lab. If you don't complete the quiz, then you won't be allowed to do the lab and you have to take an absence for that day's lab. Number 2, you'll also have to complete the assumption of risk waiver. Last I checked this morning, around 40 of you have already filled it out. Thank you for that. I have gotten emails from minors with their parental and guardian signature, but we're still missing around 15 left. So please be sure that if you haven't yet signed that assumption of risk waiver on Canvas, please be sure to do so tonight. I do need to submit it to the department sooner rather than later. For the quiz on Canvas, that can be submitted even the night before because that'll grade it by itself. On Thursday's lecture, I'll remind you all about the attire expected of you for lab on Friday, because this Friday is our first wet lab, which means that not only are you expected to come appropriately dressed, you are expected to come with your goggles. So basically, this means this is your last couple of days to try to get goggles for the lab. They are sold at the bookstore. I'm pretty sure they sell goggles at the main building over there at the front desk. If not, they do sell them on the main campus's bookstore. Those are already verified and good to go with me. If you're trying to purchase one off of Amazon or other retailers, I recommend you just reach out to me to confirm, hey, is this good to go? And I'll say yes or no really quickly. That way you're not spending money unnecessarily. Before I begin, does anyone have any questions? Yes. You take a picture of the work that you did. This particular worksheet, you're able to write the answers on the document. So you're fine to take pictures of the document itself. But as we get to more assignments, there will be some that you're going to need to write it on like a loose leaf paper or like blank paper and all that. So you just take a picture of whatever you upload. Any other questions about that? The extra credit, I've noticed that some of you have already submitted the extra credit. Just remember that the extra credit assignment is building on itself. Technically speaking, it's due the night before our first exam. So there's no way that anyone could have finished the extra credit this early. There's nothing wrong if you just want to upload it for the sake of knowing that you've done it. But remember that I'm not going to grade them until the exam. Okay. Last class, last Thursday, was a big and bold math review. During last class, when we started our first content, we talked about the different states of matter. We talked about how solids have a fixed shape and volume, for example, an ice cube. And in this case, in the case of a solid, the particles are tightly packed together and ordered, and they vibrate in place. The analogy I likened this to was an ROTC or a JROTC infantry doing their drills in the morning. Where they're moving all together as a unit, but each one is just moving in place. Liquids, on the other hand, take the shape of the container and they may have a fixed volume. In the case of liquids, the particles are close and mobile, and although there is some motion, they are limited to the container itself. Gases, on the other hand, have particles that are far apart, and as a result of this, they have high mobility. In an ideal world, gases disperse uniformly across the entire container, where this container can be something as simple as a bottle, such as a Febreze, or it can be an entire closed room, such as our classroom. There is another state of matter that has entered the lexicon as, another state of matter, but it hasn't quite really hit every single curriculum or textbook just yet. So in case you do see it online or in textbooks, the 4th state of matter is plasma. This is a high energy state with charged particles. Examples of this include stars and lightning. These are observable phenomena that do not nicely fit into one of the 3 buckets that we mentioned earlier, solids, liquids, or gases. Continuing our discussion on matter, we talked about the different classifications of matter. There are, of course, 2 types: pure. Number 1, pure, where elements do not break down chemically. You can also have pure compounds, which is two or more elements together in a fixed ratio. An example of that is H2O, which most of you may know as water, and NaCl, which you may know as table salt. If you don't know these elements already, that's fine. That will be on Thursday's lecture when we encounter the periodic table. Another form of matter is a mixture. There are two types of mixtures: a homogeneous mixture, which is defined by its uniformity. An example of that is salt water. The ocean is salty. It doesn't matter where you grab it from, how much you grab, that water is salty. That is a uniform, homogeneous mixture. In the case of a heterogeneous mixture where it's non-uniform, the best thing I can do to explain this is that they may have different concentrations or levels. For example, if you take a cup of lemonade, sometimes it might be too tart. Sometimes it might be too sweet. Sometimes it's not dilute enough. In the case of heterogeneous mixtures, they're defined by their non-uniformity. Beyond classifications of matter, we encounter various properties of matter, the first of which are physical properties. These are the most obvious. They're observable without changing composition. For example, we know that the color of my GoodNotes app on the screen at the top is blue. We know that I'm mostly using the color black for my writing, sometimes red. Another example of a physical property is melting and boiling point. This is something that you can achieve or understand just with the use of temperature, meaning you can observe when a solution melts or boils. Within the realm of physical properties, we encounter both intrinsic and extrinsic. Intrinsic properties are those that are independent of the amount seen. An example of this is color and boiling point. Whether you have an entire pool full of water, whether just you have a gallon or a gas can container, the boiling point of water is the same. By the same code of logic, if you have a blue folder in front of you, whether you rip that folder up or not does not change the fact that the folder is blue. And intrinsic is defined by its independence. That's how I remember it. Extrinsic does depend on the amount. For example, mass and volume. I am not the same weight I was last Thursday. I won't be the same weight I am tomorrow. These subtle changes is dependent on amount. It's still an observable characteristic. I can just step on a scale and figure out my mass, but it's dependent on the amount available. We then have chemical properties, which is simply defined as behavior during chemical changes. For example, flammability and rusting. Now, I want to be clear on something here. It's their ability to be flammable. It's their ability to rust that makes this chemical properties. For example, some metals burn blue, some burn yellow. The blue and yellow are colors. Those are physical properties. But the fact that those metals are able to burn is chemical properties. Following our discussion on matter, we then introduced the concept of measurements and their units. Throughout this class, throughout this semester, we'll encounter the big four measurements that kind of take the form of length, time, mass, or temperature. We use SI units, where SI stands for International Standard. I believe the origin is Germanic, so they've spelled it differently based on their language. The SI units are the standard international units that will be encountered that you can assume are the units without explanation. For example, length is traditionally measured in meters. Time is measured in seconds. Mass is measured in kilograms. And temperature, finally, is measured in K, as in Kelvin. Now, this does not mean that we'll never see a time of minutes. This will not mean that we'll see length of kilometers or a mass of grams. The simple fact is that these are the standard units that we will encounter, meaning if they're not defined, you are expected to assume these are the units. The only one you may not have been used to or ever seen before is the case of temperature, K. K stands for Kelvin, Kelvin, and its conversion is a very simple addition or subtraction. To go from Celsius to Kelvin, you simply add 273.15, such as in the case of 25 degrees, it goes up to 298.15. To go back, you simply subtract K minus 273.15, where 300.15 Kelvin is approximately 27 degrees. I do expect you to know how to convert between Kelvin and Celsius. One of the reasons why I want to make this abundantly clear is that this is actually the only conversion we will see in this class that's just an addition or subtraction. Every other conversion we'll see eventually involves some form of multiplication or division. Beyond these simple units, we encounter what are known as derived units. These are mathematical operations that are performed on those simple units to give us additional information. For example, if we wanted to calculate the density of water, it would be the mass of water divided by the volume of water. These are simple units that can be very easily measured. And by calculating this, we do find that the standard density of water is 1 gram per milliliter. Now that we have an understanding of what measurements are and the different units we'll encounter, that led us into our discussion of significant figures. Significant figures is the language that scientists will use when describing data, at least numerically. There are rules to significant figures, all of which come back to the idea of exactness. For example, number one, all non-zero digits are significant. In the case of 1.234, all 4 digits are significant. Number two, leading zeros are never significant. Shown here are 2 examples where there are zeros in front. In both cases, only the numbers 6 and 1 are significant, so 2 significant figures. Number 3, captive zeros are always significant, shown here 101.1. That 0 in between the ones is significant. We have here a total of 4 significant figures. And then finally, we encounter trailing zeros. Trailing zeros have an adage. They're only significant if a decimal point is present. They are ambiguous if no decimal point is present. An example of that is shown here when we compare both 1300 and 1300 points. Without the decimal point, this is ambiguous. With the decimal point, we're able to say exactly there are 4 significant figures. Performing arithmetic with significant figures depends on the rules. Sorry, let me rephrase that. The rule that you follow for significant figures depends on the operation you perform. In the case of addition or subtraction, you round your final answer to the least amount of decimal places. If you're multiplying or dividing, you round to the least amount of significant figures. We did a couple examples in class, and we also did that worksheet. That then led us to our final topic of last Thursday, which was scientific notation. This is a form in which you would write numbers scientifically. Scientific notation takes the form of blank times 10 to the blank, where the first blank has to be between 1 and 10, and the second blank, that power, refers to the number of jumps that the decimal point takes, where if you jump to the left, the power will be positive. If you jump to the right, the power will be negative. A couple examples are shown here, all of which revolve around us moving the decimal point to a spot where our final number is between 1 and 10. You can see here in all 3 of these cases, all of these numbers, when put in scientific notation, are 1.2. Their powers, of course, just depend on how many jumps occurred and what direction. Before I begin today's topic, is there anyone who has any questions about Thursday's content? Fantastic. Today, we are starting our discussion of Yes. Yes. Yes, I'll write it right here. Kilograms. Meters. Seconds. Yes. Yep. All right, let's dive into today's topic. We are encountering chapter 2. We will be talking, this doesn't look that nice. Let me write it. Chapter 2, atoms and molecules. Now, Thursday's lecture was very much geared towards as a general review slash catch up slash these are the basic expectations I have for you when it comes to math in this class. Today, we're going to talk a little bit about the chemistry of molecules and exactly what they are. So the first question is, of course, what are molecules made of? In the 5th century before Christ, BC, the idea was molecules were made of something called atomos, which were at the time believed to be invisible particles. That their idea was, well, it has to be made of something. Just because we can't see it doesn't mean it doesn't exist. It just means we can't see it. That was the commonly held belief. And while various people had their own ideas, for example, Aristotle believed that molecules were made of some variation of 4 elements: fire, earth, air, and water. Aristotle was a fan of The Last Airbender. But these were the ideas that were held by many scientists, philosophers, physicists, or otherwise throughout many, many years, many, many decades, many, many centuries. In some way, shape, or form, none of them were wrong, but none of them were quite right either. It wasn't until 1807 that a man by the name of John Dalton devised his own atomic theory. Dalton's atomic theory provided a theoretical framework in which to understand how molecules are made, how they're changed, and just general rules and principles. Number one, Dalton believed that matter is comprised of extremely small particles called atoms. Number two, each element has only one type of atom. What do we mean by this? We mean, well, in the case of something like a nickel penny, we assume confidently that the penny is only made of nickel. It should only have nickel atoms in it. Of course, you could make the argument that when subject to the environment and elements, it will get degraded. That's fair. But the idea is that the element should be pure of that one atom. Atoms of different elements have different properties. Oh, this one should be fairly intuitive. Thinking of something like hydrogen and oxygen, these are 2 completely different elements, hydrogen and oxygen. They're believed to have different properties. They may overlap in some way, but they're not the same. So they're not expected to be identical. Number 4, Compounds contain atoms in whole number ratios. An example of this is, of course, H2O, which we all may recognize as water. We see here what we have is what we're saying is that there are 2 hydrogens for every 1 oxygen. You will never, for example, see something like H2.1 0.9. Sure, when rounded, it's still H2O, but we always write them in whole number ratios. And then finally, number 5, atoms are conserved in reactions. Well, technically, this one Dalton stole from the physicists. This one comes from the idea, the law of conservation of matter, which states that nothing in this universe can be neither created nor destroyed, but merely transformed. Atoms are no different. If, for example, we have the following, three fictitious atoms, 3 fictitious sets of atoms, 2 green, 1 red. The products will theoretically look something like this. As follows, where I would like for you to count the number of green and red circles on either side. On the left, before the arrow, we have 1, 2, 3, 4 greens. On the right, we have 1, 2, 3, 4 greens. Before the arrow, we have 1, 2 reds. And after the arrow, we have 1, 2 reds. The idea here is that although atoms can rearrange, they must be conserved numerically. There must be an equal amount on both sides of the arrow. Now, Dalton's atomic theory, again proposed in 1807, was revolutionary in its own way. You see, prior to this moment, prior to Dalton's theory, no one had really ever written down like a clear framework to follow, a clear framework to lead or to lead with. So yeah, there were a lot of these ideas that people said, yeah, I kind of knew this already, but seeing this all together is really convenient. But over the years, over the decades, some of Dalton's atomic theory has been proven insufficient. It's pretty great. It works for like 90% of the time, but there are a few cases where it doesn't. The reason why we continue to use Dalton's theory to this day is because it's been the most consistent, meaning although other theories have been suggested, none have quite matched up to Dalton's atomic theory. So how has atomic theory evolved in the last couple hundred years? Now let's talk about the evolution of atomic theory. So Dalton came up with his framework in 1807. Around 90 years later, in 1897, a physicist by the name of Thomson, and that is Thomson without a P, discovered what he would eventually call electrons. Through his research, Thomson had identified these as being negatively charged particles. He also found through his work that these electrons were omnipresent, not omnipotent, but omnipresent, simply meaning they can be found everywhere. A little over a decade later, in 1909, a physicist by the name of Millikan confirmed the negative charge of an electron. So again, to be clear, in 1897, Thomson discovered electrons and believed them to be negatively charged and omnipresent. Almost 12 years later, a physicist by the name of Millikan confirmed his idea that it was negative. Somewhat simultaneously, a guy by the name of Rutherford discovered what he called alpha particles. And that alpha symbol that I've drawn up on the slide, on the board, or rather on my screen, is the Greek letter for A alpha. It's a little curl like that. It looks like a fish that you just haven't completed. It kind of looks like an infinity symbol. Again, just an incomplete. Rutherford believed these alpha particles to be positively charged. Now, the way in which Rutherford did this was he conducted an experiment referred to as the gold foil experiment, an image of which is shown here. Whoops. Now, I'd like for everyone to just pay attention to the screen. We're going to talk about what this diagram tells us, what its implications are. Rutherford had a very simple idea. Using an electron gun, for lack of a better word, he was going to shoot various particles at different angles, directions, and speeds through a pure gold foil, something no thicker than an aluminum foil, but gold. The idea was, heading into the experiment, would be that these particles would go through the foil and would be deflected, slowed down, et cetera, et cetera. This was the belief that the particles would split right through. While this happened, it did not happen to the degree that he had anticipated. For example, Rutherford had recognized that some particles went straight through the gold foil with no change in speed or direction. Rutherford recognized that some particles did change their speed and direction, just however slightly. And finally, he noticed that some particles just bounced back fully. So number one, some went through, no change in speed or direction. Some went through with a slight change in speed or direction. And some just did not enter at all. They were in fact bounced back. The results of this experiment led to the following conclusions. Number one, atoms are mostly empty space. This accounted for his observation that some of those particles would just shoot right through. The simple answer is that they did not collide with anything. They did not crash into anything. They just went right through. Number two, he believed that there is a dense positive nucleus at the center. Sometimes he noticed that when he shot those alpha particles, those positive particles, they would bounce right back. That is, of course, because you're shooting a positive particle and it is hitting a positive center, like charges repel. So some of those positive particles just were deflected. And number three, the nucleus is very small. This explained some of those cases where the particle was slightly affected in its speed and direction, that it did in fact hit some repulsion, but not so significant that it deflected entirely. Rutherford's ideas and conclusions laid the groundwork for what we'll now encounter as the atomic structure of a nucleus. Thanks to work laid by Rutherford, his contemporaries and other teams of scientists were over the years able to discover and identify three fundamental particles. All right, I'm going to draw a table. It's going to be a 5x4 table, so I'll give everyone a minute or two just to draw that. The headings are particle, location, charge, the mass, and again, another mass. We're going to go through the three different particles. So I'll give everyone just a few moments to draw this table up on their end. Number one, electron, one of those first particles that was discovered, is found outside of the nucleus. Remember, we talked about how that nucleus is that small center of every atom. Electrons are found outside of that nucleus. If we liken the nucleus to a planet, then the electrons are found orbiting the planet like planetary rings. Or as another example, if the nucleus is that gooey chocolate center of that Ferrero Rocher, the electrons can be found on the outside in that hard shell. The point I'm trying to make is that there is an inner nucleus and there is an outside shell where these electrons live. An electron is defined as being -1. Now, I know I've written this AMU, this mass. We're going to skip this column first. I'm first going to tell you the mass of the electron in grams. This is 9.1 times 10 to the -28. This is the mass of an electron in grams. Yes. Okay. Okay. Well, regarding the volunteer, that's open to anyone who'd like to share their notes with Aletha after each class. In addition, the transcript will be shared with you, so you're able to follow along those notes. And before each exam, I do post my handwritten notes to Canvas. That way, even if you didn't write everything down, you will have access to it in some way, shape, or form. The points for the attendance. I, I think I'm confused on what points you're referring to. You can just take a picture of the projector. You just need to take a picture that shows that you are in class. It does not need to be your particular notes. You can take a picture of the slides. You can take a picture of me, or you can take a selfie in the class.
Okay, got it.
Okay. Now, the mass of an electron is incredibly small. This is times 10 to the negative 28. We had some experience with scientific notation before. So we're talking literally 28 zeros in succession before we even get to the 9-1. This is an incredibly small number. And one thing about scientists, they're lazy. So they devised what was known as AMU, which stands for atomic mass units. This is just a conversion to a scale that is more readily understood within the context of these particles. For example, in the case of an electron, the mass is 0.0005. You'll understand the significance of these units once we finish all of this table. Number 2 is the neutron. The neutrons are located inside the nucleus. They have a 0 charge, which means that they are neutral. Its mass in grams is 1.67 times 10 to the negative 24. And its mass in AMU is 1.009. So one of the immediate things I want you to understand and recognize about going from grams to AMU is not only the scale, but the ease of understanding. Of course, we're able to look at these numbers right here, and we're able to say, well, this times 10 to the 24, the negative 24, is larger than the times 10 to the negative 28. But when you're reading all these chemical papers, a lot of these numbers, they get very confusing, and sometimes you can make mistakes. By converting it to this AMU, these atomic mass units, it's a lot easier for us to visually see, oh yeah, that neutron, that is much, much heavier than the electron. And we're able to understand that this is probably on a scale of what it looks like to be 2 to 20,000. The last particle is known as a proton. Protons are located inside the nucleus. And they have a charge of +1. Its mass is 1.667 times 10 to the 24, again in grams. We have here a situation where the numbers are very similar to one another. It's very, very slight difference. Of course, by putting it in AMU, we're able to better understand the difference. The AMU mass of a proton is 1.007. It's much easier to tell based on the AMU mass that the proton is lighter than the neutron. You do not need to know how to convert from grams to atomic mass units or vice versa, but you are expected to understand fundamentally what AMU means. It's just another scale of units that allows us to better understand the scale or mass of these particles. Now that we've covered the different types of particles encountered, let's see how they all relate to one another. Relationships. Number one, atomic number, which is given the letter or given the symbol Z. That's my Z right there, just with a line through it. Z is in zebra. The atomic number is equal to the number of protons. It is also equal to the number of electrons. Now let's think about what that means exactly. We know that electrons are negatively charged. We know that protons are positively charged. If a molecule has an equal number of both, aka both positive and negative, they cancel each other out. Meaning that in this case, this is for a neutral atom. Number two is the mass number, given by the symbol A as an apple. The mass number of an element is equal to the mass of the protons added to the mass of the neutrons. And finally, to determine the number of neutrons, it will simply be the mass A minus the atomic number Z. So what are we looking for? What does this present as, and how do we interpret that visual guide? Let's talk about a generic element symbol. For a generic element, X, you will have the mass, A, written in the top left corner. And you'll have the atomic number, Z, written in the bottom left corner. You might also sometimes have a number written on that top right of the symbol, where that N refers to charge. If no number is given for N, aka if it's absent, the element is neutral. And we, of course, know that Z is the atomic number and that A is the atomic mass. How does this help us? What kind of information can we interpret? Well, let's take a look at a few examples. Okay. Here I've written two symbols. I do not expect you to already know what that shorthand means, the MG and CA. That comes on Thursday's class. But there are a few things that we can glean from this very simple symbol. On the left, we know that the actual symbol itself is Mg. We know that its mass is 24 AMU. And we know that its atomic number is 12. We also note that since there is no charge given in the top right corner, that this is a neutral atom. If we apply this same logic to the atom on the right, we see here that the symbol is Ca. The mass is 40 AMU. Its atomic number is 20. And we see that it has a +2 charge overall, meaning it is positive. I want to point something out here. Notice that on the drawing itself, I had written 2+, but down here I'd written +2. There is no difference between the two options. Whichever way you want to write it is fine with me. They're both telling me the same thing, aka that it is positive. And that's how to read these elemental symbols, which will become very important on Thursday's class when we finally go over the periodic table. As with every rule, as with every theory, as with every framework, there will always be some form of exceptions. In the case of atoms and molecules and their symbols, the only exception is what's known as an isotope. An isotope, or rather isotopes, are atoms of the same element with a different number of neutrons. One of the most popular examples of an isotope is carbon-12 versus carbon-14. Carbon-12 is our standard. It has an atomic number of 6, has an atomic mass of 12. This is the standard, the most commonly found version of carbon. In this case, we can calculate the number of neutrons as 12 minus 6, which gives us 6. In the case of carbon-14, it still has an atomic number of 6, but its mass is 14. In this case, the number of neutrons will be equal to 14 minus 6 to give us 8 neutrons in total. So carbon-12 and carbon-14 are both carbon atoms with a different number of neutrons because of their different masses. Carbon-14 is actually very popularly used. Does anyone know what carbon-14 is used for? Maybe in the context of a museum? I see a hand over here. Fossils? What about fossils? How old they are. Carbon-14 is regularly used with dating old archaeological artifacts, objects, and the like. The idea is that they're able to study and identify the amount of carbon-14 present and use that information to determine the age of something. This is most commonly used in museums or historical societies. For example, if you want to find out the age of a mummy. This is similar in theory to if you've ever heard of trees, and you can, when you chop down a tree, the number of rings tells you its age. It's the same thing here. Carbon-14 is used to date archaeological artifacts and the like. In fact, isotopes are everywhere. Almost every element has some. For example, hydrogen. Hydrogen has 2 isotopes, the first one being deuterium. And the third, right now, I'll leave the name blank, but I will give it to you in a few moments. Hydrogen, of course, has the following symbol, H11, where its number of neutrons is equal to 0, 1 minus 1. Then we have deuterium, which has a mass of 2, such that its number of neutrons is 2 minus 1 to give us 1. And then we have that third that has a mass of 3, leading to a number of neutrons as 3 minus 1, aka 2. Now, this particular isotope is less known. However, if you're a fan of popular culture, you may know it. More specifically, if you've ever watched Spider-Man 2 with Tobey Maguire and Dr. Octopus, you know exactly what this element is. For absolutely 0 points extra credit, does anyone want to tell us what is the name of the element that Dr. Otto Octavius used in Spider-Man 2? When he said, "The power of the sun in the palm of my hand"? Does anyone remember? We usually have one person in the class that knows this. No? That's all right. The name of the third element, third isotope, sorry, is tritium. To kind of give you context to the scientific accuracy of Spider-Man 2, everyone here might already know the story of the hydrogen bomb. The hydrogen bomb is one of the most notorious cases in history where upon exploding the nucleus of an element, it led to a pretty significant explosion, because the idea at the time was that hydrogen could have been seen as a fuel source, as an unlimited energy source. Spider-Man 2 took that to another level to say, well, let's look at another isotope of hydrogen, tritium, and let's apply it to the same logic. It can also be a source of abundant power. But we all know what happened in Spider-Man 2. It exploded. Chances are the same is going to happen if anyone ever tries to look at deuterium. So now the question is, well, if all of these atoms exist, we've just looked at hydrogen and carbon. I've told you that there are many different isotopes for many different elements. The question is, how do we know which one we should focus on? Do we need to worry about every single isotope? Why is it that we never really see the tritium and deuterium in our language? The answer just comes back to statistic probability. With different types of metals, different types of elements, you carry out what are called atomic mass calculations. You see, you're absolutely right. When we mine these different types of elements, when we mine something like carbon, there is a chance that what we're mining is carbon-12 as well as carbon-14. How do we know which one we're dealing with? How do we know which one is the standard? Well, to do that, we would calculate the average mass, which is equal to the sum, that's that Greek letter epsilon, capital, I believe, the sum of the fractional abundance multiplied by the isotopic mass of the element or isotope in question. What exactly does this mean? Well, let's do a sample question. The question will read, calculate the average mass of boron given the following information. Boron with that symbol, atomic mass 10, atomic number 5, was mined and found to have a 19.9% abundance. This particular version of isotope is also known to have exactly 10.0129 AMU. Another isotope was found. Again, boron 5, but its mass is now 11. This has approximately an 80.1% abundance, which has a mass of approximately 11.0093 AMU. These percentages just quite literally refer to the statistics of finding these elements / isotopes. Meaning if a mining company were to dig and dig and dig and try to find boron, out of their entire collection, 20% of it would be the 10, and 80% of it would be the 11. And we know as scientists exactly what those AMUs are, so we have that information at the ready. With this, we can then calculate the average mass. It's equal to the abundance, 0.199, times the atomic mass, 10.0129. And we're looking at the sum of both of these products. Notice that the percentages, obviously they're percentages. I've immediately divided them by 100 to get rid of the percentage. You could have, of course, just written 19.9 over 100 times the 10.0129 and so forth. It would still be the same thing. But the key point here is that it is the sum of the fractional abundances multiplied by the masses. If we put this into our calculator, we get exactly 10.8780601. And between you and I, we all know that we're not going to report this in a paper with all of these decimal places. What are we going to do? We're going to reduce the amount of appropriate significant figures. Here we have a situation where we have both multiplication as well as addition. Multiplication is based on least amount of significant figures. Addition is based on least amount of decimal places. So which one do we listen to? I'm here today to tell you that no matter what, always multiplication and division take priority. So let's take a look. From left to right, how many significant figures in 0.199? That should be 3 SF. In the case of 10.0129, we have 1, 2, 3, 4, 5, 6. All of those zeros are captive. Then we have 0.801. This is 4 significant figures, right? No, it should be 3 significant figures. Why? Because there is a leading zero, and leading zeros are never significant. This zero right here in the middle is captive, so that's good to go. And then we have 11.0093. This is a whopping 6 significant figures. Off the bunch, the lowest number does appear to be 3 significant figures. It doesn't matter which one you base your logic off of because they're the same, 3 significant figures. Looking at the number we did calculate, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. And we have to reduce this. How do we reduce this? Well, we start counting from left to right. We count the first 3 significant figures, 1, 2, 3. After the third significant figure is what tells us if we should round up or round down. After the 8 is a 7. That's what tells us we should round up. This becomes 10.9. Do we have any questions? Yes, question? Sure, we can talk after that. Yeah. Yes, you would follow classic math rules, which is brackets first, then multiplication, division, then addition.
The same things.
Mhm.
I thought we do like multiple.
Good question. You don't do the addition at all. When given a choice, like in this case, you have multiplication and division. Multiplication division rules always take priority, and that's flat. Meaning you follow those rules and that's it. Yeah. Any other questions on this? Okay. That's it for today. Pretty short lecture. When we come next on Thursday, we're going to go over the periodic table. I will print a copy of the periodic table for everyone. So the next time I see you, we're just going to talk about what the periodic table is, how to identify the elements, electrons, blah, blah, blah. I'll see you guys on Thursday. If you have any questions, come talk to me now. If not, I'll see you in a couple days.